Welcome to this explainer. Today, we're going to dive right into the fascinating, hidden science behind the everyday sounds all around us. From the simple hum of your refrigerator to the intricate melodies of your absolute favorite song, sound is this invisible force of energy that's constantly shaping our reality. But what exactly is it? How does it actually physically move through the air to reach our ears? And honestly, what hidden powers does it hold when we push it way beyond the limits of human perception? Let's find out.
Here's our quick roadmap for today. We'll be hitting 1. The birth of sound. 2. Riding the invisible wave. 3. Decoding sound characteristics. 4. The science of echoes. 5. Sounds we cannot hear. And finally, 6. The power of ultrasound.
All right, Section 1. The birth of sound. How vibrations create what we hear.
So, let me ask you this. Can you produce sound without a vibrating object? Well, the short answer is absolutely not. Try clapping your hands right now, or just gently touch your throat as you're listening to me speak. You'll quickly realize that all sound requires mechanical energy to create a rapid to and fro motion, or in other words, a vibration. Whether it's a plucked guitar string, a struck tuning fork, or even just the flapping wings of a bird, you literally have to set an object into rapid motion. That vibrating object is the absolute starting point. It's the spark that ignites this entire invisible symphony.
Moving on to Section 2, riding the invisible wave, the mechanics of propagation. Okay, so once that vibration happens, it needs a way to actually travel, right? Sound absolutely requires a medium, like a solid, a liquid, or a gas. It doesn't work in a vacuum. There's no sound in empty space. Imagine the vibrating object acting like a tiny, super-fast piston in the air. When it shoves forward, it pushes and crowds the air particles together, creating this tight region of high pressure called a compression. Then when it pulls back, it creates a region of low pressure where those particles spread way apart, which we call a rarefaction. This sets off an alternating domino-like chain reaction of high-pressure compressions and low-pressure rarefactions that travel all the way through the air right to your eardrum.
And that whole domino effect brilliantly illustrates why sound is classified as a longitudinal wave. Think of playing with a slinky. If you push and pull it, the coils move back and forth in the exact same direction the energy is traveling. That's exactly what sound does, physically pushing and pulling the medium. Now, this is fundamentally different from a transverse wave. Actually, a good way to picture a transverse wave is dropping a pebble in a pond. The water ripples up and down, perpendicular to the outward direction the wave is actually spreading.
Section 3. Decoding sound characteristics. Anatomy of a wave.
Now that we know how it moves, we really need to break down the specific anatomy that makes each and every wave unique. I mean, why does a flute sound so different from a heavy drum? Well, it all comes down to these core characteristics. Every single sound wave is defined by its wavelength, which is just the physical distance between two compressions, and its frequency, meaning how many of those waves pass a specific point in 1 second. Throw in amplitude, which dictates the loudness based on the sheer force of the vibration, and all these elements seamlessly, mathematically combine to determine the pitch, the loudness, and the overall speed of the wave.
To put that speed into perspective, think about these numbers, because it's pretty mind-blowing how dramatically the speed of sound jumps as we move through different states of matter. We generally think of sound moving through the air, right? And in standard room temperature air, it travels at roughly 346 meters per second. But look at aluminum. Because the particles in a solid are packed so tightly together, the sound wave transfers its energy way more efficiently. It literally rips through solid aluminum at a staggering 6,420 meters per second. That is vastly faster than in the air we breathe.
Let's move to Section 4, the science of echoes, reflection and reverberation.
You know how a rubber ball bounces off a wall? Well, sound waves do the exact same thing. We've all shouted into a canyon just to hear our own voice bounce back, but to hear a distinct, clear echo, some very precise mathematical conditions have to line up. See, your brain actually holds on to the sensation of a sound for exactly 1/10 of a second. So for you to hear an echo as a totally separate, distinct sound, the reflected wave has to return to your ear after that 0.1 second window. In normal air, this means the reflecting wall must be at least 17.2 meters away to allow for a 34.4 meter minimum round trip.
But you might be wondering, what happens when those walls are a bit closer and the sound just keeps bouncing around? If sound bounces around too much, like say in a huge empty auditorium without any soft draperies or sound-absorbent ceilings, it creates a highly undesirable effect known as reverberation. All those multiple reflections blend together, creating this really muddy, prolonged persistence of sound that makes it incredibly hard to make out distinct words or music. All right, Section 5, sounds we cannot hear. beyond human limits.
So, what happens to the sounds that are simply too high or too low for us to detect? The absolute upper limit of a healthy human ear is 20,000 hertz. That means 20,000 wave cycles per second. And our baseline starts down at around 20 hertz. If a wave oscillates slower than 20 times a second or faster than 20,000 times a second, it is completely invisible to our ears. But let me tell you, there is so much more happening outside this narrow little window.
The crucial takeaway here is that there's a massive, invisible symphony constantly playing all around us. Just below our hearing range is infrasound. These are massive, deep waves used by rhinoceroses, whales, and elephants to communicate over miles and miles. It's actually even the frequency range of the deep rumbling warnings generated right before an earthquake hits. On the flip side, anything above 20,000 hertz is ultrasound. These are rapid, high-frequency waves utilized by bats, dolphins, and even rats to navigate in pitch black, hunt for prey, and communicate with each other.
And finally, Section 6, the power of ultrasound, real-world miracles.
The most exciting part? We aren't just casually listening to this physics anymore, we're actively using it. Because high-frequency ultrasound waves don't easily bend around obstacles the way normal sound does, we can fire them in precise, perfectly straight lines. This allows engineers to literally safely peek inside solid steel blocks to detect microscopic, invisible flaws that could otherwise bring down an entire bridge. And in medicine, it's a total game changer. Doctors use these exact same waves to clean microscopic circuitry, safely image a beating human heart through echocardiography, or, get this, even break down painful kidney stones into flushable grains without making a single surgical incision. I really hope this explainer has completely changed how you think about a simple hand clap or the everyday hum of your own voice. Sound is just so much more than what hits our ears. It's this highly structured transfer of mechanical energy with the power to cross oceans, image the unborn, and reveal hidden flaws in solid steel. It really makes you wonder, doesn't it? If we can do all of this with sound, what other incredible unseen forces are quietly shaping the world around us, just waiting for us to figure out how to harness them? Thanks so much for exploring the fascinating physics of sound with me today.